Good afternoon, ladies and gentlemen. Welcome to you all. This is Mert Oytun speaking. I'm a master's student and a research assistant in the civil engineering department at the Middle East Technical University. Today, I will present our research entitled Assessing Existing Buildings for LEED Retrofit, a case study of a university building. Here is the outline of today's presentation. First, I will try to give the background information and our motivation for the study. Then the methodological details will be explained. After that, the findings will be discussed. And finally, I'm hoping to conclude my presentation with the highlights of our work. So let me start with the introduction part. Throughout the history, the soaring of greenhouse gases emissions greatly concerns the architectural engineering and construction society on how to provide a sustainable built environment. This is because 35% of natural resource use and around 40% of greenhouse gases emissions on the universe globally caused by the applications related to the construction industry. This concern led to establishment of green building rating systems like LEED and BREAM in early 1990s. Accordingly, both researchers and practitioners conducted green building concept-related studies with different concentrations. In developed countries, the green building applications in both newly constructed facilities and renovation projects are already consolidated. But in developing countries like Turkey, the importance of these concepts has been recently understood. In this sense, here in Turkey, there is a lack of sustainability-related studies, especially concerning existing education buildings. Therefore, we aim to assess the sustainability potential of an existing university building in our research. Moving on the methodology, first, the building's existing condition is analyzed to understand the building characteristics. As demonstrated in the figures, the building is massive. Including the parking space and green area, the size occupied by the building is more than the size of a soccer field. Moreover, approximately 1,500 people use the building in a day. The three-story building is made of reinforced concrete. The 29% of the building facade is covered with glass, and the building has 120 rooms in total. In terms of mechanical and electrical systems, the building is centrally heated and don't have mechanical ventilation system. And the indoor illumination is achieved with manually controlled bulbs. Secondly, aiming to assess the sustainability potential of the existing building and to develop an understanding whether LEED retrofitting is cost efficient or not, data is collected through first, on-site observation and walkthroughs. Second, interviews with administrative staff. Third, the document analysis. And fourth, the market price analysis. Since the building is relatively old, the exact quantitative data was missing at some points. Therefore, a couple of realistic assumptions are made in the given 5 categories, like the general, location and transportation, water efficiency, energy and atmosphere, and indoor environmental quality. The further details of these assumptions can be found in the manuscript. But let me give some examples on this. It's assumed that the vehicle owners don't use alternative transportation modes. Moreover, the occupants' daily building usage durations assumed to be vary according to their social status or social roles. What I mean is that the daily building usage durations change if an occupant is a student or an employee. Thirdly, the building's existing condition is assessed based on the LEED V4 for O plus M schools checklist. It was remarkable that points acquired for the location and transportation is very high in the current situation. It can be seen in the table. On the other hand, the low performance for the water, energy, and indoor environmental quality make us realize that these categories need to be improved. As a result, 28 points are acquired for the existing condition from all the categories. Hence, at least 12 more points are needed since the minimum required point to get LEED certified is 40. Accordingly, potential improvements are studied. In the LEED checklist, some categories have preconditions, namely prerequisites. They are needed to be eligible to be evaluated for the certification process. Therefore, these improvements are primarily selected. For the location and transportation, to increase the alternative transportation usage rate, preferential parking spaces are planned to be labeled. For the water and efficiency, the following improvements are suggested. They have 32% of water use reduction potential in total. The individual contributions are also shown in the parentheses in the text. In terms of energy and atmosphere, the proposed energy-saving system replacements provide around 33% of reduction in the energy use. And for the indoor environmental quality, air quality alarm installation, adjustable electrical switch replacement, and daylight measurement device installation are considered. Before starting this part, I would like to mention that even if we aim to measure the sustainability potential, we had to use the monetary equivalent of the improvements as a measurement tool in our analysis. This is because our world is mainly dominated by money. Back to the topic, the proposed improvements are evaluated by performing two different analyses. First one is the cost benefit, and the second one is the cost efficiency. The main difference between these methods is that cost-benefit analysis is profitable in the long run, while cost efficiency offers the cheapest solutions based on the initial costs. The calculations are conducted based on annual equivalent cost of the improvements. It's because these improvements have unequal service lives. Furthermore, first, the estimated initial cost, second, the expected incomes, third, the maintenance cost, and fourth, 10% of constant interest rate are considered throughout the calculations. Benefit to cost ratio and total initial cost to point potentials ratios are calculated and used in the identification of the possible improvements for the analysis. In short, the highest values were always the leading ones for the identification process. These are the used equations in the calculations. You can check them if you want. And this table summarizes the findings of the study. The blue ones, the metering installations, are the prerequisites, so they need to be implemented first. The red highlights, which are dominantly related with the water and energy, are the improvements proposed considering the findings of the cost-benefit analysis. And the yellow ones are the cheapest solutions dominated by the indoor environmental quality. They are suggested based on the results of the cost efficiency analysis. In this table, I want to mention a point. As you can realize, some of the benefit to cost ratios are zero. This is because these improvements don't have an income potential which is considered as the benefits in the study. Here is a further comparison of the findings of two methods. In the comparison, we realize that social benefits of the improvements are also needed to be considered. However, their monetary value representation were not possible in these analyses. Ultimately, as it can be followed, the total initial costs differ for two methods, while the point potentials are the same. This reveals that improvements in cost-benefit analysis are profitable in the long run due to the expected incomes, while the rest offers the cheapest solutions to get LEED certified only. In a nutshell, in this study, the sustainability potential of Metro Civil Engineering Department's main building for LEED retrofitting is assessed. The aim was to collect minimum required score to get LEED certified and to raise awareness for educational facilities. To do so, first, existing condition of the building is analyzed. And second, the potential improvements are identified. Following, these improvements are assessed for both cost-benefit or life cycle cost and cost efficiency perspectives. The results of the cost-benefit analysis show that the priority should be given to water and energy-related improvements. On the other hand, location, transportation, and indoor environmental quality-related ones come to the fore based on the cost efficiency analysis. Considering the use purpose of the building, as a limitation in this study, only minor retrofits are considered to not to take the building out of service. So, major ones may have greater potentials. As a future work, we suggest that social and environmental aspects of the retrofitting should also be analyzed besides the analysis in this study. All in all, the findings of this study reveal that initial cost of sustainable LEED retrofitting in educational buildings can easily be compensated thanks to the reductions in the resource usage. So, I guess this is all for today. Thank you so much for your invaluable participation.